Good morning and welcome to today's T&D World webinar titled Unlock the Future of Grid Intelligence, Discover Aware, sponsored by PDI Squared in partnership with Southern California Edison. I'm Nikki Chandler, Editorial Director for T&D World with Endeavor B2B. To begin, let me explain how you can participate in the session. First, if you have any technical difficulties during it, please submit that to the questions window and all technical experts can help you out. We recommend disabling any pop-up blocking software or extensions in your browser, as that can sometimes cause issues with that webinar player. Additionally, we do welcome your questions during the event today, and we'll answer as many of those questions as possible during the Q&A session or even throughout this discussion. Just feel free to send in those questions at any time. To do so, just simply type those questions into the question window on the side of your screen and hit submit. To refer a colleague to today's discussion, share it on social media, or access event resources and click the icons on the left side rail of your screen. Also, just a tip, to resize your windows for a better view, you can click on that upper right-hand corner to enlarge on your screen there. Please be aware that today's session is being recorded and will be available on the T&D World website within the next 24 hours. You'll be notified by email when that archive is available. All right, I want to go ahead and introduce Mike Beeler this morning. He's the national spokesperson for the Power Delivery Intelligence Initiative, or PDI Squared. And I'm just going to hand it over to you, Mike, to introduce our guest and to lead the discussion. Thanks for being here.
Well, thank you, Nikki. It's a pleasure to be here. We got a great topic today. I want to start off by saying, what is the Power Delivery Intelligence Initiative? We're a group of contractors and consultants and vendors and equipment manufacturers that advocate for underground. We want planners and engineers and data scientists to take a look at underground as a very viable option and alternative for what might otherwise be an overhead transmission or mostly distribution line. So why are we talking today about this particular topic? And these are the various members of the Power Delivery Intelligence Initiative. Why are we talking about this topic? Well, one of the things that PDI Squared does is we encourage innovation and creativity as we look for ways to apply underground principles across the T&D spectrum. And our friends today at Southern Cal Edison have done that, and they've won a very prestigious award for it. So I'd like to just tell you that we've got two great speakers from Edison today. Vic Trahan is the Vice President at Southern Cal Edison. Vic, give us a quick hello, if you would.
Yes, good morning, Mike. Good morning, team. This is Vic Trahan, Vice President of Transmission Substation Operations. Quick background for myself is started as an engineer more than 20 years ago. Along the way, have led multiple teams such as engineering, asset management, and most recently grid operations.
And with Vic is Hamed Valistahagi, and Hamed is one of the award winners with Vic on this AWARE program. Hamed, give us a quick word of welcome this morning, if you would, please.
Thanks, Mike. Good morning, everyone. This is Hamed Balizadeh. I'm a technical lead at SC. I have a PhD in intersection of AI and power systems, and it's been a pleasure kind of working on this system together with Vic. Looking forward to the conversation today.
Yeah, Hamed, what a fascinating thing to get a PhD in as a combination of AI and operating systems. So we're really eager to hear from you guys. And this is an award-winning concept. The award was given, it's the Edison Award by the Edison Electric Institute. It's their most prestigious award that's given every year to a single investor-owned utility. And this year, like in some previous years, Southern Cal Edison has won this award for what Vic and Hamed are going to explain to you today. So we're really proud of the Power Delivery Intelligence Initiative to share this with you today and hope that you appreciate it. So Vic, with that introduction, I will hand it off to you and let you say a few things, and then we'll have a conversation about what you guys are doing at Edison.
Yeah, thank you, Mike. Appreciate it. Good morning, folks, again. And hey, let's just keep this discussion as a conversation and interactive. Now, along the way, if you have any questions, please post those, and we will try our best to address those. So first and foremost, thank you for joining us today at this T&D World webinar. And we certainly appreciate the opportunity to share Southern California Edison's journey towards building the grid of the future. One that is not only intelligent, but more resilient and safer for the communities we actually serve. I am super enthusiastic to introduce you all to AWARE, which is Advanced Waveform Anomaly Recognition. It's a mouthful, I realize. But at its heart, AWARE is about one thing, and that is visibility. Seeing that has been invisible all along. And this is basically done by transforming raw data into actionable intelligence, and then utilizing this intelligence to detect disturbances before the cascade. I have always said this isn't just all about technology, but it's about empowering our team members, system operators, engineers, line crews with the foresight, rather than having to react on the hindsight. With a system like AWARE, we are not just waiting for outages to tell us, what's a problem or there is a problem. We are basically making all the efforts to read between the signals coming from the grid that have been there all along. It's just that we never had the technology to detect those. So again, we are excited to talk about AWARE and how AWARE basically is improving grid operations, through this technology, through this system, how we are patching traditional technologies with nuanced technologies like AI, machine learning, to boost resilience and fulfilling our commitment towards, again, I said, the most important aspect of our jobs is the communities we serve. So thank you again, and let's dive in. All right, so this slide just basically shows the table of content that both Hamad and I will cover. So we'll start with essentially the traditional distribution grid. So let's start with where we have been. So looking at this system, the traditional distribution grid was built again for a very simple system. It was linear, limited, reactive. Power flow was one way from the substation to the customers. Minimal sensors, coming from the grid, limited and latent, communication protocols, and in a sense, the recovery was slower. In this model, we had blind spots everywhere. Essentially, we were waiting for something to break or anomaly to happen before we would know something is broken, right? So the legacy design here was built for more so yesterday's challenges and not for tomorrow's complexities. So let's talk about what's changing, right? Today, the world is evolving and changing pretty rapidly. The emerging distribution grid is alive, I would say, with a two-way power flow and inundated with new technologies such as solar, wind, batteries, EVs, microgrids, digital substations, grid hardening, covered conductors, DERs, as I mentioned, solar, wind, and EVs and inverter-based resources are literally rewriting the playbook, as we go along. Advanced sensing and visibility is no longer optional for sustainability, and novel, and available grid technologies are progressively enabling a stronger, safer, and more adaptive grid. So from where we stand, it is evident that the opportunities are immense. But along with the opportunities, there are significant complexities. This grid basically demands, not just the infrastructure, but also intelligence to be able to successfully run.
Vic, what's interesting is several years ago, Edison put out a white paper called Reimagining the Grid. So is AWARE part of that? I mean, the picture you're showing right now about the emerging distribution grid looks like a reimagined grid. What are you building upon that white paper or that whole concept?
Oh, 100%. And then, the beauty of AWARE is it's an organic element of the white paper. It's not just AWARE that we're investing in. We're also investing in smart grid management systems. We're also in the middle of basically launching our advanced distribution management system, And we are also putting a lot of investments to bolster the infrastructure as well by putting in more field sensors like automatic reclosures and remote switches. Also, we are envisioning the AMI 2.0. And the beauty of all of this is that these, unlike the technologies of yesterday, where, these systems were standalone, siloed, going forward, they will all be integrated and work as a collective system in tandem. So 100% to your question, Aware is a part of that vision. Okay, so before I talk about the Aware system, I always like to kind of keep it at three key questions, and what are the key drivers? I always say why, what, and so what. So we just in the previous slide we talked about how rapidly the grid is evolving, and as a part of this evolution, there's one key challenge. And that is detecting and locating the complex grid faults with accuracy and timeliness. Particularly, I'll talk about the California grid. In order to literally mitigate wildfires, we're investing into insulated conductors. But the challenge that comes along with that is if you do have a down conductor and the conductor is insulated, it will result in a high impedance fault, meaning that you would have minimal short circuit current, and the conventional protection technology may not be able to detect those conditions. And this is where technologies such as Aware, they come in. So again, the question is, what exactly is Aware? As I had mentioned previously, Aware stands for Advanced Waveform Anomaly Recognition. So this is an in-house built, physics-informed AI predictive analytics platform that basically listens to the grid at the very, I'd say, DNA or the waveform level in near real time or real time. So the question would be is what exactly is a waveform, right? And the way I always exemplify or run some analogies there against the waveform is think of waveform as an EKG or a heartbeat of the power system. So Aware is a technology that basically is sensing on the waveforms coming from the grid sensors, coming from the substation digital fault recorders, coming from automatic reclosures, coming from the relays. And the innovation essentially is combining this waveform intelligence with the other standalone grid data from these various sensors, and then augmenting and applying AI ML algorithms to predict the precise location of the fault. One key advantage of Aware is, its ability to not only just detect conventional faults and then predict the precise location of that fault, but also detect, incipient or early stage faulty conditions prior to them turning into something significant or potential outages. Think about there's a pattern on a power system where maybe the distribution capacitors are turning on and off, and as a result of that, it's burdening the system. And you may see this incipient, transient, that we have not been able to capture through conventional platforms, but now with Aware, we are getting this information, we're getting this data, and with the power of AI ML, we are able to basically latch onto those patterns and then predict, what's bound to happen in the near future. So essentially, the bottom line here is instead of waiting for the outages to occur, Aware essentially detects anomalies, predicts these failures, and literally guides our crews to the exact location of the problem, faster, safer, and with precision.
So it sounds like, Vic, you must have a massive number of sensors on your overhead and underground system that brings you a vast amount of data that you're able now to go through and really extract the valuable information out of that to be able to ultimately take action.
100%. Mike, that is I'd say a challenge and a blessing, by itself. So over the years, and through various initiatives in grid modernization, we have invested in, the field sensors. I always say, a grid management system, a technology such as Aware, is the brains of the power system, and these field sensors, the isolating devices, automatic reclosure, circuit breakers are the muscles of the power system. So, but along with that, so much of information is coming in, and along with the information, to make sense out of that information becomes challenging. And this is where the power of AI ML comes to the picture. So yes, I would say, the blessing is that we have deployed a lot of sensors. The challenge has been is how to drive clarity from the information coming from the grid. All right. So, again, in the end, when we innovate, the innovation basically has to have a value proposition, right? So, understanding the impacts is critical as we design intelligent systems like Aware. And here, as you can see, the impacts are real. So far, I'd say, as an example, we evaluated close to a handful subset of incidents, and Aware has successfully tracked more than 300 incidents with over 80% accuracy. I mean, that is something, right? That basically means, again, in layman terms, that basically means that hours were saved on every outage, right? And from a safety mindset, think it through. Most importantly, by virtue of knowing what the anomaly is, what the problem is, where the problem is, this system has been able to underscore or support enhance public safety of our crews who are being dispatched to go and investigate those issues, and the communities that we are basically serving, by allowing us to proactively, well, first and foremost is detect those conditions, and then proactively mitigate those dangerous conditions before they escalate. In many cases, we are able to basically go back and address those concerns, and address those anomalies, before our customers are even aware of, whether something's brewing on the power system, no pun intended. So, pinpointing the failures faster, uh, directly allows, targeted repairs, which basically then reduces the outage time. The result is, improved customer trust factor, with fewer disruptions. And if disruptions do take place, then faster remediation, faster restorations.
Right. Those are great points, Vic. Let me ask you a question too. So you say 80% of these outages are predicted ahead of time and basically prevented. So the beauty of artificial intelligence, if I understand it correctly, would be that you can further refine, and maybe get even a higher percentage as you start to tweak your algorithms. Would that be correct?
Oh, 100%. That's a very insightful statement, Mike. As a matter of fact, we're already embarking on, right now we're working on a concept. We have, select number of sensors that we are, harnessing the waveform data from. So far, we have 26, 27 some substations where we had installed, these fault recorders for a different use case. But now we are basically just streaming the data to, our system and running AI ML algorithms with real information coming from these sensors. Imagine a world where we're able to utilize, now what we have the algorithms in place, we're able to utilize synthetic data coming from RTDS testers, right? And then we do invest in our IT systems, and we do install infrastructure both in the field and at the substations. We can scale this up immensely, and definitely that is within our plans. But that's a great question, though, Mike. One thing I'd say, the challenges that I can attest to, not only just Southern California Edison is facing, but our partner utilities and across the country are facing, it's not that the demand is not just bolster reliability, boost resiliency, but also bring the cost down. There's and with Aware, with the technology such as Aware, there is a significant element of affordability as well. Knowing the precise location of the fault, and even just addressing faults before they turn into a catastrophic failure, allows us to optimize our resources. This will basically allow us, to have a more targeted dispatching, avoiding unnecessary truck rolls, and eventually basically reducing the cost of restoration. So that is a huge factor and huge benefit, coming from a system like Aware. Simply put, aware, either way I see aware is a bridge that essentially turns data into a foresight, and then foresight turns into increased reliability, public safety, and customer experience. So with that, I'll quickly see if there are any questions. Doesn't look like we have any. And I will hand it over to Hamed at this point.
Thanks, Vic. I'll just jump right in, talking more about the data types. As we all know, we have fancy artificial intelligence, machine learning, and the compute to empower it. But to be completely frank here, it all comes down to the data. And if we don't have the type of data that supports the training of those models, these systems would not be happening. Now, from the data types perspective, really the one core element for aware is the waveform measurements. And these are high fidelity, high resolution waveform measurements, both in a continuous manner. So the device, the one Vic mentioned, the DFRs, are measuring continuously the disturbances and anything that's happening on the voltages and currents at a very high resolution. Or we have event-based data, as you can see on the left side of the screen. This is one example of that. So it's basically looking for transients that are kind of above a certain threshold and capturing the pre-fault, post-fault, and event duration of those transients. And this really helps aware to detect anomalies and characterize them. And as I'll dive deeper into how that happens, it's basically looking at these transients, and it is able to categorize the type of event, what happened in the power system, like if it was underground cable failing versus animal fault versus another thing. So that's the core data type. And again, that comes with lots of challenges in terms of handling that complex data, in terms of training AI and ML models to be able to kind of do the things that I mentioned. The other part of the equation is the edge sensors that we've leveraged the current AMI systems for. Our current AMI systems are capturing this kind of, I would say, imperfect capture of the transient, meaning if the voltage on the meter side of it goes above or below a certain threshold, it's going to log that and in real time sends back. So aware also leverages that. I'll explain the way that's essential for our pinpoint fault location in the whole aware system. And last but not least, we also have our grid data, SCADA events, etc. That also really helps put the whole puzzle together in terms of event modeling. We'll look into architecture a bit more in the coming slides.
So Hamed, my mind is racing ahead on this particular slide. If I'm a utility out there listening to this, I said, well, I'm not Southern Cal Edison. I don't have the number of sensors deployed that I need to get the vast amount of data that Hamed says I need. But if I do have advanced meter infrastructure and I do have SCADA, is that a place where a utility can start with a concept like this?
Absolutely. So one of the beauties of aware actually is it's relying on scarcity data. So meaning if there is a limited amount of information, so for example, I would wish that we had the next generation AMI to go with this system, but we made the best of what we have in terms of these real-time exceptions that are coming in on the voltage. And same thing goes with all sorts of data. First of all, we can adapt this to the existing sensors on any utility system. And if you have, like, let's say, instead of a DFR, if you have a power quality monitor, that can be leveraged. If you have some waveform measured at a relay, that can be leveraged also. So it's really about getting the most out of your data. And again, the physics-informed AI ML, is helping with that.
It's kind of funny, Hamed. It sounds like you've already got a wish list for new sources of data like AMI 2.0 or something.
Absolutely, and again, this system is really looking forward into those future systems as well, because the combination of a centralized AI and ML with edge devices, basically, so you put both kind of analytics at the edge and at a centralized location, and this combination is perfect for what it's kind of the environment we are at right now, but also it just adapts really well into that future and taps into that.
And Mike, if I may add on to what Hamed was saying, is solutions such as digital vault recorders, they are not as expensive. Unlike the sub-transmission system, or distribution DFR is relatively cheaper in cost, and it's minimally disruptive. So at a substation with, say, 10 distribution lines, hypothetically speaking, we can easily install a DFR system, and you wouldn't even have to take outages. A lot of times these DFRs come with what we call a split core CT, so you can basically just install them, plug and play, and at least you have that intelligence coming from the substation level. In the future, if for certain companies, if the systems are connected and you are able to pull in these, waveforms or oscillography from the system relays, that also becomes, very helpful in programming and training an algorithm like this. Now, as you had mentioned and Hamed has mentioned, is as we are putting together what capabilities do we need for the future AMI, one thing that we are looking into a better sampling rate and the capability to basically have oscillography and waveforms at the edge level. So when we basically combine the intelligence and information coming from both the source, which is a substation, and the edge devices, we are able to make better, more precise predictions.
Absolutely, and basically these devices are, we have also within Aware built the pipelines to support these types of devices. So again, that's also a foundation that will kind of help streamline the process of installing these sensors as they become also abundant and leverage into the algorithms. So I would just start at a high level to kind of introduce the architecture behind Aware by categorizing the backend analytics into three categories, basically. So it's the waveform analytics. Again, as we talked about, that's the core part of the whole system, starting from the waveforms and looking into those different anomalies. And then the integration of sensors across the system into the waveform anomalies that are being detected, that's another key part of it to give the system context in different events that's happening. And then the final kind of ultimate piece is boots on the ground, basically, and locating the anomalies and classifying the anomalies. That those anomalies could be, again, different types of faults, could be even a normal condition. We want to recognize that and not have false positives. So that's also part of that. So I'll kind of explain a bit more on the operational components. Just want to introduce, we have a front-end system, a dashboard and notification system, but also this system should integrate with our other processes. In grid operations, we have different use cases. There are use cases that would benefit from even detecting the normal device metrics. And all of those are coming from centralized event modeling. What we've seen with Aware is having edge measurement and edge analytics is really critical, but also that centralized piece of putting the whole modeling together for events, that's really key. And as you can see in this diagram, we have our own database of waveforms that are measured from the DFRs. We are bringing in the edge data, the SCADA live circuit models, grid connectivity, and different algorithms that I'll introduce more in the next slide that are targeting anomaly detection, signature detection. Those are feeding into a centralized event modeling. And we also close the feedback loop from the ground truth to adapt the model the AI/ML would learn from it. So this is basically a snapshot of main components for AI and ML part of the whole equation. And as you've seen, as you see on the slide, we have like 3 major steps to enhance this AI and ML. Basically, the reason it's tricky to apply AI ML in realistic systems is usually the noise of the system and the false positives you get. And again, for what we do, we are really close to the field, and we want to retain the trust with the field. So really the tolerance for false positives is low. However, there are steps we could take, and we've made it happen with Aware, is to make the AI and ML really accurate through augmentation of features and extracting the proper features and expert knowledge. And when I say augmenting expert knowledge, it's not just people looking or engineers looking at the data. Rather, really, we've taken the expert perception of the transient and the grid and augmenting that into the AI and ML. So it's really helping with the process. So the process itself is going from the raw waveform on the left-hand side, transforming the data. So basically, an AI and ML would not look at the raw waveforms, rather a transformation of those. And again, that suppresses any sort of background noise, and it really augments the features that we want the AI and ML to learn from. And it minimizes the need for labeling and basically improves performance significantly. And the same thing goes with the other modules: anomaly detection, characterization, combining those with the power grid attributes and edge sensors, which again results in that ultimate step of knowing what the event was and locating that. And both of those final steps really have expert knowledge augmentation to counter any sort of data imperfections or model performance issues. In the coming basically 5 slides, I'll be diving deeper into different components on this diagram. So basically starting with what type of transformation on the waveforms is happening within Aware. Again, as I mentioned, it's really trying to augment and enhance the signature itself. So even some of these signatures even are invisible to the naked eye. If you look at the waveform, it's really hard to see if something happened on that like sinusoidal waveform. And these are on screen. These are the synthetic data. The real data we are dealing with really has the noisy behavior, the higher order harmonics. That's going to be causing problems for the AI and ML. But then when you have the proper transformation, in this example, I'll skip the details of it, but in this example, if you, for example, leverage wavelet transform instead of a FFT transform, or together with FFT transform, you're going to be looking at a very enhanced feature that the AI and ML can tap into and can learn from. So this basically supports those 2 next steps: anomaly detection and characterization. As this slide shows, the anomaly detection is all about providing features that it's not only about having thresholds that basically if a certain threshold is passed, you are going to be flagging it as a problem. Rather, this basically feeds into the anomaly characterization step as well. I'll talk more about that. So we were looking at 2 features to enable a proper anomaly detection step. To make it successful, we built an anomaly detection feature that has dynamic range. What that means is, for smaller problems, you get a smaller magnitude of the features. For bigger problems, for high energy incidents, you get a bigger value. Even the type of transient that's distinguishing between, let's say, arcing versus harmonics, you need to have this feature basically have different magnitudes for that. The other aspect of this step is really to make it super sensitive, because as we talked about different use cases, really those subtle signatures, because we want this model to be predictive, looking at the early stages of the failure for any certain equipment, the signatures are going to be really subtle. So making the super sensitive is going to be able to pick those up and make it available for AI and ML. The other piece is the anomaly characterization. And again, I want to emphasize this goes together with the detection. It's not like we are running the anomaly detection on its own and then be done with it and then move on to the characterization. The features that are feeding from the anomaly detection, the same features feed into the anomaly characterizations as well. Now, with the anomaly characterization, there's a lot of data to kind of tap into. You see this picture here. It's basically goes forward in time. If you notice the visualization guide from basically left to right, goes down on y-axis, and every kind of block of this is you looking at any sort of transient that's happening on the grid. Could be normal operation, could be anomalies, and the features that are being visualized on the screen are telling the AI and ML which anomaly is that. And then according to your labeled data, they are being trained. So basically on the historical data, they're being trained, and then the same sort of parameters applied for new situations. It's almost like the modern chatbots. They have the history of information, data from different books, internet, and now when you ask a question, they kind of bridge the links and provide you a prediction. It's exactly the same thing with this AI and ML as well. It's just in this context, these features are physics informed to make the system super accurate, super reliable, and the embedding of the information is really about the power systems data. This is another example of how we bring in the edge sensor. So with the AMI, it's really, this example shows how it really supports and helps fault location, meaning because you have the AMI distributed across the system, if you pattern match spatially and temporally with the basically the waveform information that you've transformed, gone through the anomaly detection and anomaly characterization steps, then by pattern matching, you're going to be able to assign a certain cluster of meters to a certain cluster of anomalies. So like if you look at that red circle, when that matching happens, then you have a location. I'll kind of introduce more in the next slide what that looks like. Here you can see, again, this is just one scenario and one example, but you can see kind of the matching materializing on a layout of a grid. And you get a pinpoint location for sending the crews, and they would investigate. And in our experience, more than 80% of the time, they found the same problem that's being forecasted by Aware. Basically, this is the last piece of it. So we know at this stage of Aware detection, we know where the problem is, and we know the nature of the problem. And we can even prioritize based on the detection. If it's a underground cable issue, maybe just a heads up in the early stages, maybe just a heads up that to the crews that there is some issue underground. If you are doing some work, be careful. Or maybe it's a pinpoint location that we can send the crews to mitigate and prevent an outage down the road.
Hamed, I've got to interject a question here. So when you tell the crews that, hey, we think there's a problem there, do they look at you and say, no, there's not a problem there, that system's running fine? And then you come back and say, no, we really think there's a problem. You explain to them a little bit about what you're doing, or you just say, go there and take a look at that, or be careful? How's that interaction work?
Yeah, no, that's a great question, and that's why our group really has a really close relationship with the field, because these new systems, it takes kind of building that communication style. So a big part of this aware deployment strategy we kind of went through was us basically telling them this information in a way that basically based on our past experiences, relationship with the field, they would kind of go exactly do the investigation the way that this system tells us to perform, basically. And this is another example of it, actually. This slide shows the process of incipient faults materializing in an underground component. When you look at this from months ahead of time, Aware can still detect that anomaly, can also label it as an underground issue. The problem is, because the signature is very subtle, it's not going to give you a pinpoint location. And that changes over time. So like maybe days ahead, weeks ahead of the final failure, you are going to get a pinpoint location. So in this case, and during the pilot, we basically only sent out crews when we got this pinpoint location, and they would go and directly find the issue. For the months ahead, we just gave a heads up, and we basically communicated according to the detection itself. We would say there might be an underground issue in the back half of the circuit. Heads up. And I'm going to move on to my last slide before handing over back to Vic. I want to emphasize these 5 core components here. I'm going to actually start from the last one. Really, we want these models, the AI and ML models, to be explainable. When I say explainable, that really means that the nature of the machine learning is that they are treated as a black box. But that's really not appropriate for engineering precise systems that we have. So then your features are physics informed, and Aware is really tapping into showcasing the reason behind every detection. So if there is a underground issue being detected and predicted, it's not a black box that Aware somehow detected. We can trace back the decision of Aware into those features, and then later on to the engineering aspect of it. So you can basically, again, tune the algorithm over time and maintain the trust. The other piece here is we don't have much labeled data in this space. So one of the big challenges we had to overcome, you need to have really well-engineered AI and ML to not rely on an extensive set of labeled data. That's another issue. There are public labeled data. We do our own labeling, but again, the amount is minimal. So really, some of these AI and ML models would need to be well engineered to not basically derail because of that limited amount of labeled data. And then complex data, we talked about, both Vic and I talked about a lot, but then also integration into our system is complementary in this case, and it should be. We are covering a gap. We are not basically going and reinventing the wheel in terms of some of the basic systems that are working. As far as this looks into the future, you can do that eventually when the data, the infrastructure supports it. But it's really about seeing the visibility gaps and tuning the AI and ML in a shape or form that sees and covers those visibility gaps. I think a similar discussion can be applied with DERs in terms of controllability gaps. But this is only at this time looking at the visibility gaps of basically resulting into a better anomaly detection and anomaly characterization. And I think that would be much more evident talking about the challenges. Vic?
Thank you.
Hey, Vic, let me just interject a quick question here, and you both probably can address it. The question from the audience is this system running live? Or is this a delayed data type of system? Or is it running live?
Yeah, today Go ahead.
Oh, sorry. Go ahead, Vic.
No, I was going to say today, I did see Steve's question here. So today, the way the system is designed is it is running after the fact. But the after the fact actually depends on, it could be a couple of hours after, it could be one day after, or it could be, as Hamed said, when you're seeing patterns, it could be a few days before the system detects that, hey, something is brewing, something is going on.
Interesting. Thank you.
And from a more future real-time decision-making perspective, to really address Steve's question here, is we are envisioning, at full maturity, we are envisioning to basically integrate Aware into our novel advanced distribution management system. So the thought process, the vision, or the goal would be is, once the confidence level is 100% or near 100%, and then you have an anomaly notification coming from Aware system, then you would just basically isolate that system instantaneously. Okay, so moving on, as Hamed talked about, when you build a system like this, which is really dependent on amounts and amounts of data, you come across significant challenges as well. So as we were set up to build Aware, the challenge really wasn't that we didn't have data or the data was too little. It's the opposite, actually. We had too much of the data, and as you can imagine, a waveform recorder coming from a sensor can produce up to, multiple gigabytes of data on a daily basis. So the question really wasn't about, are we able to store this much of information? It was more about the clarity of how do we basically drive, teams, patterns, intelligence, towards a decision making. This data itself added a lot of challenges to what Hamed was saying. Is different sensors and different systems from the field, from the substations, didn't always align, and and that resulted in creating of some noise and lack of clarity and uncertainty. As you all can imagine, where if there is a blip on the system, if there's a transient on the system, incipient faults could be there for milliseconds and then disappear. So sometimes that could be as a result of a nuisance, or sometimes that could be a real hazard. Animal making a contact, or maybe an insulator basically giving out signals prior to a failure. It became hard to basically just create models to detect those situations. And every anomaly looked unique, looked different. As Hamed so eloquently mentioned, is a signature coming from a potential underground cable failure was different, as compared to an overhead arcing, or even, animal making a contact. The signals were there, but knowing, which ones really mattered and which ones to prioritize was definitely a challenge. And, starting on a project like this from a clean slate, so having to build these fault catalogs and training the MI, AI ML models on a perpetual basis to distinguish between what truly is a meaningful signal versus what is a noise, definitely pose some challenges for us. And again, as earlier in the conversation we mentioned, that we are relying on technology that was implemented prior to this mindset of integration. So we had information coming from these siloed sensors. So the placement of these sensors became an issue. Was it really optimally placed that would give us the most intelligence? The coverage of telecommunications in the network at that location, that sometimes had challenges, and sometimes the measurement itself was not perfect. So one element we talk about challenges is the actual talent itself. Is we needed experts with not only just the domain knowledge of the power systems, knowledge of the automation both at the field and at the substation level, but strong data science skills to build a system, a technology that is reliable, and that would basically give us minimal false positives. So certainly I would say that is the resources and the type of resources to propel this forward was a challenge for us as well. So in spirits of time, I'll quickly just conclude, and maybe if you have time, we can take some questions. And if you're not able to address all the questions, please reach out to us, and Hamed and I can make every effort to get back to you to make sure that we respond to your questions. But in conclusion, I'll basically say that inside all these challenges and complexities lies the opportunity. The solution wasn't, as I mentioned, more data, is to basically how do we shape this data into a more intelligent format or more smart format. This is where the power of AI came to the picture by combining the AI machine learning algorithms with physics modeling and human expertise. I'd say, as Hamed talked about, literally Aware was able to differentiate and transform noise into into a foresight. Aware, as it stands today, isn't just detecting anomalies. It is recognizing patterns. And once we realize these patterns, it's basically guiding us towards a faster and safer decision making. Through Aware, we are able to basically move from a really having reactive protection-based mindset to a prediction-based mindset. Going from reacting after an outage has taken place to really thinking about what's happening so we can prevent an outage to begin with. As I mentioned earlier, with hardware technology such as RTDS testers and filling in the blanks with the availability of synthetic data, we can now simulate, anticipate, and respond before customers can even feel the impact of significant real life events as well. And at the heart of this whole innovation is the trust. Want to really underscore this sentiment where Aware isn't about replacing human expertise. As a matter of fact, human expertise is at the crux of this innovation. It's about amplifying it. Our crews, engineers, operators, they remain at the front and center of this innovation. Just empowered by more intelligent tools and deeper insights. And again, the result here is by investing in technologies and innovations such as Aware, Grid just doesn't operate. It's perpetually learning. A grid that adapts and improves with every single event and incident that it basically sees.
Well, Hamed and Vic, that was we probably could have gone for another half an hour. We got a few audience questions, and I've got a couple here, but we're at the top of the hour almost. So I got to ask one audience question. Where do you house all this data? Are you doing this internally on servers at Edison, or do you use cloud-based servers?
This is on-prem, so internal. Due to the sensitivity of some of this data, we couldn't leverage cloud, and we have built our own pipelines customized for the application.
And that was the gist of the question about sensitive data coming off the system. So, good. Now I have a last question. T&D World Magazine just had a big article on the Eaton Fire rebuild. You guys made a pretty big announcement that you're going to rebuild everything underground. So now you've got a blank slate. You're going to rebuild an underground system. How are you going to do it? You're going to build it. You must have a list of sensors that you want to have to maximize the value, I would say, of the Aware system. Have you thought about that?
Yeah, Mike, 100%. So as we are rebuilding, we are being very conscious and mindful of how we design. Our engineers and field engineers, distribution engineers are as they're designing, they're keeping this in perspective that it's going to be a combination of hardware, software, and intelligence. So placing the sensors at the most optimal locations in the future, AMI 2.0 on the onset, and the utilization and maximizations of technology such as ADMS and Fizzr, and coupled with or empowered by technology such as Aware is going to be the future.
That's fascinating. Hamed, we're almost to the top of the hour here. If you've got some concluding remarks, please share them with the audience today and give your final comments.
Thanks, Mike. Yeah, so this system, I think, is really cutting edge and basically looking into what's possible with AI and ML in an engineering and grid operations context. And really, it was kind of uncharted territory for us to be able to make this as successful as it become. But it was also very rewarding. So a really exciting system to build, really kind of this is really close to us to talk about. So again, as you said, Mike, and Vic, would be happy to kind of answer more detailed questions later on. And thank you all for listening.
Thank you, Hamed, and congratulations on the big award. I know you are a real foundational part of that. So really, really interesting stuff. Vic, give us some concluding remarks and comment a little bit about the innovation culture that you've got at Edison. Just one more time, if you would, please.
Yeah, thank you, Mike. I appreciate it. Well, first and foremost, my most humble gratitude to T&D World for this opportunity. Definitely recognize the fact that we as an industry are at the forefront of once in a generation transformation of the electric grid, and working in a silo is not going to get us there. So forging a very united coalition is going to be the name of the game. Coming together and sharing ideas and exchanging ideas and building this grid of the future, intelligent, reliable, and resilient, is going to be the framework going forward. Just super ecstatic and thankful for the award, one of the most prestigious awards in the industry. So we are really humbled by it, and we are excited by it, and we're energized by it. We want to keep going, and we want to keep going, via this correlation that we're going to build in the industry. One sentiment that we've always shared is, at the end of it, the bigger story here is complexity really isn't our barrier. It's more of a catalyst. And at Southern California Edison, we genuinely believe in, the grid of the future isn't just waiting for us. We have to build it. So breaking the silos, having a platform where engineers, data scientists, they bring in these ideas to us, and giving them the opportunity and the framework to explore these ideas, being courageous, being innovative, investing in our labs, investing in our resources, participating in the industry. I think that's all of this is going to be critical as we embark on this journey. And just most importantly, I would say it's not just about the infrastructure, it's not just about the investment, it's not just about all technology itself. Something that is very personal to me, and I feel that Southern California Edison really empowers it, is starting with a clear vision, understanding the value proposition of why we are doing this, and what is the benefit to our company, what is the benefit to our customers, and what is the benefit to the industry, and then instilling a deep passion to make it happen.
Well said. I wanted to say that on behalf of the Power Delivery Intelligence Initiative, we are really excited about what you're doing with AWARE at Southern Cal Edison. You won this prestigious Edison Electric Institute Edison Award this year, and again, you have won it before because you do have a very innovative and creative culture at Southern Cal Edison. One of the things that you said that I really appreciated, and I know, Vic, this is your background, and Hamed, this is right up your alley as well, is that you were working with the men and women in the field to make sure that they understood what you were doing with this very advanced technology. They probably hear about artificial intelligence all the time, but what is it? And you're actually helping them apply it in the field. So congratulations to you both. Well done today. A great webinar. And I'm Nikki Chandler. On behalf of the Power Delivery Intelligence Initiative, we say thank you to T&D World Magazine, and I'm going to hand it back to you.
Thank you so much, Mike. What a great discussion today. This is really an exciting project. And thank you so much for sharing that with us and our audience today. For any questions we didn't really have time to answer, we will be getting back to you via email. And that does conclude the session today. On behalf of T&D World, I would like to thank Mike, Vic, and Ahmed, PDI Squared and SCE for being in today's and sponsoring the webinar. And of course, all of you for joining. Thank you again, and have a great rest of your day.
Thank you.